Pre-calculus 2.6 day 1. We're looking at rational functions. And rational functions are where you have a polynomial over a polynomial. And so you're going to be finding domains, finding vertical and horizontal asymptotes, and be able to sketch the graphs of these rational functions. And one of the original rational functions is f of x equals 1 over x. I don't know if you recall kind of what that looks like, but it looks something like this, where we have vertices of 1, 1, and negative 1, negative 1. Basically, if I think of this as y is equal to 1 over x and I multiply by x, it's products of two numbers, that is 1. And so any two numbers that multiply to be 1, those are going to be possible xy ordered pairs. And when you look at this, since it never hits the y-axis, it has a vertical asymptote there. And so we have vertical asymptotes. And for vertical asymptotes, the function can never cross it. We're going to see in this first example, it's because there are x values that are limited from the domain. Right here, the domain on this is all reals except for 0. I can't let x be 0 because I'd be dividing by 0. So we'd say the domain's negative infinity to 0, union 0 to infinity. And since x can't be 0, there will never be a point on that y-axis. And that's the nature of a vertical asymptote. So the function will never cross, touch, have a point on a vertical asymptote. But we also have the ends, and really horizontal asymptotes are about end behavior. As this continues to go to the right or continues to go to the left, that function follows the x-axis. And it gets closer and closer, but never actually reaches it as x gets really large or really super small. And those are known as horizontal asymptotes. And sometimes it is possible for that rational function to cross a horizontal line, but it usually happens more in the middle. Because horizontal are about end behavior, so the ends will get closer and closer, but in the middle, it sometimes can cross. We probably won't see a lot of that, but it is possible, so I thought I better mention it. So anyway, so there is a rational function, and so that's kind of what we're going to be doing here is graphing those. So let's look at example number 1. Find the domain of y is equal to 4 over x minus 2, and discuss the behavior of f near any excluded x values. And right here, the denominator cannot be 0, so that means x cannot be 2. So the excluded value is 2. And so we want to discuss the behavior of f near that excluded value. And so if I think about the domain, it's all reals except for 2. It's just what we have to eliminate what makes the denominator 0. The domain's negative infinity to 2 union 2 to infinity. And so what I have you do is this little sign chart, and we're going to put on here any zeros. We don't have any zeros in this case, or any undefined places, which are the excluded values. And that is 2. And you are going to, when we graph this, eventually, we're not graphing it in this example, but you would have a vertical asymptote. So I'm just going to write vertical asymptote above that. And basically what that does is the function has to, if you're graphing it, you're graphing to the left of 2 and you're graphing to the right of 2, and you got to pick up your pencil and graph as you change from the left side to the right side of 2. And so that causes an opportunity for this function to change signs. And so we want to discuss the behavior near any excluded x values. And basically at x equals 2, so on the graph of this, so at x equals 2, that vertical line x equals 2, which is this vertical asymptote, the end behavior can be going to negative infinity to the left of it, or it could be going to positive infinity on the left side of 2. So we describe that as x, oops, that's supposed to be as, x approaches 2, and on the left side, we want to know what y does. Is it going to negative infinity or is it going to positive infinity? And then we're going to do the same thing. So describe the behavior of f near any excluded values. I also want to look at this as x approaches 2 from the right. So as I approach 2 from the right, is y going down and following the vertical asymptote by going negative infinity? Or is y going up and approaching 2 as we approach 2 from the right and going to positive infinity? That's basically what we're looking for. So what happens if we come back to this kind of number line kind of thing is it breaks f into intervals. And it's just divided by that excluded value. There's only one excluded value, so we just have 2 intervals. And basically, I just want to test a value to the left of 2. And so if I would put 1 into the function, and so that function is 4 over x minus 2, so I have 4 over 1 minus 2, would be 4, it's positive divided by negative, it's going to be negative. And that's basically all I need to know. I just need to know if it's positive or negative. So what that means is to the left of 2, this entire rational function is negative. So guess what? It must be, since it's negative, it's got to be that bottom choice. And so as we approach 2 on the left side, since the function's negative, y must be going to negative infinity. So let's test the other interval. So to the right of 2, pick a number in that interval. I would just use 3. If I plug that in, you basically, it's just the sign that I'm worried about, not so much the value. And if I have a positive divided by positive, it's going to be positive. So to the right, this rational function is going to be positive. It does, the only excluded value is 2, and there are no zeros, and we'll talk about zeros later, but there are no zeros. And so since to the right of 2, this rational function is always positive, I know that the end behavior must be that it is approaching positive infinity. That must be what's happening. And so that y value must be going to positive infinity. So that is kind of how we can look at the behavior near an excluded x value. All right. So now we're going to look at definitions of vertical and horizontal asymptotes. And vertical asymptote is when you have an excluded value and the y values go to positive or negative infinity as x approaches that from the right or from the left. And so really when we're going up here, this means approach 2 from the left. And this right here means approach 2 from the right. And notice that the end result was y is either going to positive infinity or negative infinity. That's what always happens with a vertical asymptote. On either side, y is either going to positive infinity or negative infinity. And that's what this is describing in number 1. And second is a horizontal asymptote. And this is saying that the y values approach a specific height. And that height is b, as x is going to positive infinity or negative infinity. So it's for really large values of x or really small, large negative values of x, that the function is approaching a specific height. And those are horizontal asymptotes. But there's some things about vertical and horizontal asymptotes and that are good. And so we have d of x is your divisor, your denominator, and n of x is your numerator. And the graph of f has vertical asymptotes at the zeros of d of x. We saw that in example 1. In example 1, d of x was that x minus 2, and the zeros of x minus 2 is when x is 2, so we have a vertical asymptote at x equals 2. So that's simply how you find vertical asymptotes. Set the denominator equal to 0 and solve for those. At least that's where they will be. And sometimes we'll tomorrow or the next day we'll talk about some special cases of that. And number 2, the graph has one or no horizontal asymptotes determined by comparing the degrees of n of x. Determined by comparing the degree. And so the degree of n of x and d of x, the degree of n is that leading coefficient's power, and the degree of the denominator is that leading term's power. So the degree of n is capital N of x is n, and the degree of d of x here happens to be m. And so here are 3 cases. If the numerator is smaller in degree than the denominator, then you have a horizontal line of y equals 0. When the degrees in the numerator and denominator are the same, then you have a horizontal asymptote. That is the ratio of these 2 leading coefficients, y equals a sub n over b sub n. And when the degree of the numerator is greater than f, there are no horizontal asymptotes at all. So those are things to memorize. So when the numerator is smaller degree, y equals 0 is always your horizontal asymptote. When the degrees are the same, it's the ratio of a sub n to b sub n, y equals that is your horizontal. And if the numerator has a larger degree than the denominator, there are no horizontal asymptotes. So you need to memorize basically those 3 possibilities. So find all vertical and horizontal asymptotes and then graph this function. And so on f of x here, for vertical asymptotes, I need where the denominator is 0. And so if we factor that, x plus 1, x minus 1, the zeros of the denominator are -1 and 1. And so my vertical asymptotes, they are equations of lines. They're x equals -1 and x equals 1. Those are my vertical asymptotes. Those are my excluded values. At -1 and 1 on either side as we approach left from the left or from the right, either y is going to positive infinity or negative infinity. And so those are my vertical asymptotes. So that is part of your answer because they asked for it. And then for horizontal asymptotes, notice that the degrees of the numerator and denominator are the same. So for horizontal asymptotes, the degree of the numerator, so n is 2, and the degree of the denominator, which is m, is also 2. And since when the degrees are the same, then the horizontal asymptote is that ratio of a sub n over b sub m. And the a sub n is that 5 and the b sub m is 1. It's that coefficient of your x squared terms. So the horizontal asymptote is going to be y is equal to 5 over 1, or we would just write y is equal to 5. So there is my horizontal asymptote. Y equals 5. And so then we are going to graph this. And so you're going to kind of need to figure out the domain and zeros. So we're going to look at what we call key numbers. And key numbers are what makes the numerator equal to 0. So 5x squared equals 0 when x is 0. And what makes the denominator 0? So that x plus 1, x minus 1 equals 0. That happens when x is -1 or 1. And so my key numbers are -1, 0, and 1. And what I'm going to do is I'm going to put those on a number line. And so I've got -1, I have 0, and I have 1 for this function f. And as I did in the first example, what makes the denominator 0 is going to create vertical asymptotes. But what makes the numerator equal to 0 actually makes the overall rational function 0. That is actually a 0 for the rational function. When x is 0, the y value is 0. So this is going to cross the x-axis when x is 0. And so as I go, it said find all vertical and horizontal asymptotes of the graph of each rational function. And so I was going through and thinking in terms of graphing these. And I guess it didn't actually ask for graphing, so I kind of got a little bit ahead of myself. So we actually have the vertical and the horizontal asymptotes already gotten here. But while I'm on this roll, let's look at what would the graph of this kind of look like and what would we go to do from there. And I'm going to consider the domain of this. And so the domain, the excluded values are my vertical asymptotes. The excluded values are those vertical asymptotes. What makes the denominator 0? So I have to, all reals except for -1 and 1. So my domain, -infinity to -1, union -1 to 1, union 1 to infinity. Notice the 0 is an included value. It's just what made the denominator 0, which created vertical asymptotes that had to be eliminated from the domain. So that's something that you should kind of know. And anyway, what you do to graph this is we check to see in each of these intervals on this number line whether this rational function is positive or negative. So we have a -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. By the time when we identify these key numbers, what makes the numerator 0, what makes the denominator 0, those are the only chances, those places for this function to change from positive to negative. And so once I've got those, I know I just have 4 intervals to check to see if this function is positive or negative. And I pick a test number in each of these intervals. So the left -1, I'd use -2. Don't use the endpoints themselves. Between -1 and 0, I would use a 1/2. Between 0 and 1, I'd use, or that should be -1/2. And between 0 and 1, I'd use +1/2. And to the between 1 and infinity, I would choose 2. And then what we do is we just check out the factored form. We have 5x squared over x plus 1, x minus 1. And we just check out what the signs are for each of those by plugging in -2. And if I put a -2 into this 5x squared, it would be positive. I don't need the value, I just need if it's positive or negative. If I plug -2 into this first factor, it would be negative. If I plug -2 into the third factor, it would be negative. And that would make it positive divided by positive, and it is positive. So that graph's positive there. And -1/2, if I plug that in, I get a positive over a negative, and this function's negative there. And if I plug in a +1/2, it's positive in the numerator, positive for the first quantity, and still negative for the second. So that's going to be negative there. And then if I plug in 2, I get a positive in the numerator, I get a positive, and also positive when I put 2 into x minus 1. So this function's positive. So my sign graph on this goes positive negative, negative, and then positive. So if I go to sketch this, I know it didn't ask for it, but I started going that way, so I went ahead and just kept on with it. I have a 0 at 0. And then at -1, I have a vertical asymptote. And at +1, I have a vertical asymptote. And then don't forget that I have a horizontal asymptote up at 5. And so now what I have happening here is to the left of -1, this function's positive. So the function must be going to positive infinity there and then approaching the horizontal asymptote there, because the function has to be above the x-axis, but end behavior has to approach the horizontal asymptote. And to the left of -1, since it's a vertical asymptote and the function's positive, y has to be going to positive infinity. Between -1 and 1, this function's going to do this. Because it's negative on either side, but just comes up and touches 0 at 0. And on -1 on the right, since the function is negative, and that's a vertical asymptote, y has to be going to negative infinity. And at +1 on the left side of +1, since the function is negative, y has to go to negative infinity there. And to the right of 1, since the function is positive, y has to go to positive infinity. And then since the horizontal asymptote is 5, the function has to follow it there. So that's quite a bit for the first one, and part of that was just because I got a little carried away with find all vertical and horizontal asymptotes, and essentially that was just by setting the numerator equal to 0 and the denominator equal to 0, and that's pretty much what it asked for. So I just got too excited about that one. All right, so let's move to this next one. And so some guidelines are in here for graphing. Simplify the rational expression if possible. Find and plot the y-intercept by evaluating f of 0. Find the zeros of the numerator. Plot those x-intercepts. Find the zeros of the denominator and sketch the corresponding vertical asymptotes. 5, find and sketch horizontal asymptotes by using the rules that we did in the last section example. And then plot at least 1 point between and 1 point beyond each x-intercept and vertical asymptote. So on this one, sketch this graph and state its domain. Well, we can give the domain right away, because the only thing I have to be concerned about is what makes the denominator 0. And excluded value in this case is that -5. X can't be -5. So it's all reals except for negative and -5. So the domain is this. And 2 over x plus 5, so number 1, simplify. It already is simplified. Find and plot the y-intercept by evaluating f of 0. And that is 2/5. And so 2/5 at 0 is going to be just kind of right there. So just kind of have to estimate 2/5. So we have that y-intercept. So you can write that way or 0, 2/5. Either way is fine. And so we've done that. Now find the zeros of the numerator. And this numerator can never be 0. This numerator is always positive. It's a +2. It doesn't have a variable. So this numerator is never 0. So there are no x-intercepts. There are no x-intercepts when the numerator doesn't contain a variable. And so we've done that. Number 4, find the zeros of the denominator by solving for x plus 5 equals 0, which we did earlier. And this is going to be a vertical asymptote because it makes the denominator 0. And so at -5, we are going to dot a vertical asymptote. And we're expecting, certain behavior to the left side of it and to the right side of it. And so what I would do for that is create a number line for the graph of f. And at -5, I'm going to call that as a vertical asymptote. And since there are no other zeros, and that's my only vertical asymptote, that divides this function into two intervals, from -infinity to -5, and from -5 to +infinity. And basically what I'm going to do is pick a test number to decide if the function is positive or negative in each interval. So to the left of -5 is -6. Between -5 and infinity, I would use 0 since it's in there. And then basically what we're going to do is figure out the sign of this rational function. And in this case, the numerator is always positive, and if I plug in -6 to the denominator, it's negative, and positive divided by negative is negative. So to the left of -5, this function's below the x-axis, and it's going to be negative. And if you plug in 0 into this, well, the numerator is always positive because it's a +2. And if I put 0 in the denominator, I get a positive, and positive divided by positive is positive. And so to the right of the vertical asymptote, this function is positive. So at that vertical asymptote, since it's left to the left of -5, it's negative, I know that this rational function must be going to -infinity on the left side of -5. And to the right of -5, since it's positive, I know that this graph must be going to +infinity on the right side of -5. Excuse me. And now this has no zeros. And so I have one other thing to consider here. So I've done the zeros of the denominator. It's, well, maybe a couple more things, but number 5, find and sketch the horizontal asymptote, if any. Oh, well, in this case, for horizontal asymptote, the degree of the numerator is 0. Because I can think of this as f of x is 2x to the 0th over x plus 5. X to the 0th is 1. So when it's a constant, the degree of that is 0. And the degree of the denominator is 1, because it's x to the first. And when the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is always y equals 0. When the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is y equals 0. So for end behavior, this function is going to follow this x-axis. So we're getting these pieces of the puzzle put together. Number 6, plot at least one point between and 1 point beyond each x-intercept. Well, there were no x-intercepts, so plot at least 1 point beyond each vertical asymptote. Well, we already have this 2/5 on the right, to the right of the first. So this vertical asymptote is just going to come, and it's getting really close, and it's just going to continue to follow it. There are no x-intercepts, so it just follows as end behavior. As x gets large, it's just getting closer and closer to that x-axis. And then to the left, we don't have a point plotted, so I want to pick a point to the left, and I've got 2 over x plus 5. What if I put in negative, how about -8? And so we have the 2 over x plus 5. So I get 2 over a -8 plus 5 is 2 over -3, so a -2/3. So at -8, you're at a -2/3, so you are already way up here. So, but I have no x-intercepts, so I just have to get closer and closer to that x-axis and follow it to the left. So there's a lot to it, and you have to get better at it by practicing and just kind of go through the list. Use smooth curves to complete. These polynomials are smooth, well, they're not continuous because we had asymptotes, curves. All right, so let's look at one more. Sketch this graph. And so, first of all, simplify if possible. There's not anything to really simplify with 2x plus 1 over 1 minus x squared, other than you could write it as 1 minus x and 1 plus x. You're going to need to factor it anyway to find the zeros. And then number 2, find and plot the y-intercept. Oh, we didn't talk about domain. I forgot about domains. Let's look at domain. And x can't be 1 or negative 1, because that would make the denominator 0. Your excluded values are 1 and negative 1. And so we have negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. And that's the domain for this, because we have to skip over 1 and negative 1. And then find and plot the y-intercept. So f of 0, 2 times 0 plus 1 over, I'm just going to plug it into the original equation. It'll be faster. And you get 1 over 1, which is 1. So f of 0 is 1. So we've got 1 point there. And the next step is to find the zeros of the numerator and plot corresponding x-intercepts. So set 2x plus 1 equal to 0. And if you solve that, you get x equals a negative 1/2. So you have an x-intercept of negative 1/2 comma 0. So put that in right there as a point. And I'm going to go ahead and box that. And then you're going to come back here and find the zeros of the denominator and sketch the corresponding vertical asymptotes. So we already found 1 minus x, 1 plus x equals 0 when x equals 1 or negative 1. So my vertical asymptotes are x equals 1 and x equals negative 1. And so we're going to go ahead and draw those. And then after you find those vertical asymptotes, sketch horizontal asymptotes by using the rule. And for horizontal asymptotes, you need the degree of the numerator, and you need the degree of the denominator. And the degree of the numerator is 1, and the degree of the denominator is 2. It's a negative x squared. The highest power is your degree. And in this case, the degree of the numerator is smaller than the degree of the denominator. So the horizontal asymptote is y equals 0. When the degree of the numerator is smaller than the degree of the denominator, that horizontal asymptote is 0. So again, end behavior is going to follow that x-axis. Remember how we said you can cross horizontal asymptotes in the middle? That x-intercept crosses the horizontal asymptote, and that's perfectly fine. It's not a problem. Horizontal asymptotes are about end behaviors. So x-intercept, vertical asymptotes, horizontal asymptotes, a y-intercept. I forgot to label that. Those are all things that you're going to need to be able to identify. Now, to sketch this, I am going to do a number line, and I'm going to use all my key numbers. And the key numbers are the zeros and the values that we had to skip. The back up here, we call those the excluded values, the excluded x values. So, so the zeros and excluded values, the vertical asymptotes, are my key numbers. And in this case, that is going to be -1, -1/2, and 1. So they kind of come close together, but I can kind of spread them out on here. We have vertical asymptotes at -1 and 1, but at -1/2 we have a 0. And so what I want to determine is this function positive or negative in each of these intervals? So I kind of didn't give myself quite enough room here. So I have my intervals, and since there are 3 key numbers, there are 4 intervals: -∞ to -1, -1 to -1/2, and -1/2 to 1, and 1 to infinity. And so you pick a test number. So -2, -1 to -1/2. Oh, I'm going to have to use -3/4. And -1/2 to 1, I can use 0, and 1 to infinity, I can use 2. And then basically what I'm doing is putting those into the factored form, that 2x plus 1 divided by, I'm going to have to do it this way because I ran out of room. And so if I plug that in, I'm going to get a negative divided by, if I put -2 into 1 minus x, I get a positive. And if I put a -2 into 1 plus x, I get a negative. So overall, you get negative divided by negative, which is positive. If I put a -3/4 in, 2 times a -3/4 is a -3/2. A -1 and 1/2 is going to be negative. If I put -3/4 into 1 minus a -3/4, it's going to be positive. And if I put -3/4 into 1 plus -3/4, it's going to be positive. So we have that it's negative there. And if I put in 0, well, I already checked when 0. That was my y-intercept, and the y-intercept is 1, so I already know it's positive there. Then I put in 2, I get a positive, divided by 1 minus 2 is negative, and 1 plus 2 is positive. So that's going to end up being negative. So I've got positive, and negative. And so I have to remember end behavior. And in this whole first interval from -∞ to -1, it's positive, so the graph's going to look like this. It's got to follow the horizontal asymptote as x goes to -∞, and it's going to have to go to positive infinity as it approaches -1 from the left. And then in that small interval from -1 to -1/2, the function's negative, so it's just coming down, and it's just going to follow that asymptote. There's not much more to show that. And then in between, it's going to have to do, it changes concavity somewhere in there. It's the only way it can do it and follow, because it's going to have to go to positive infinity, because from -1/2 to 1, the function's above the x-axis, it's positive. So it looks like that. And then to the right of 1, it's negative. So that means as you're approaching 1 from the right, y must be going to -infinity. And there are no other x-intercepts, but as x gets large, since the horizontal asymptote is 0, we have to approach from underneath. So there's quite a bit of analysis to this. And you can check your work on Desmos's or a graphing calculator or with answers in the back of the book. But if you don't sit through and try to analyze it and learn the process and make your brain go through that, you're not going to be able to do these quickly and accurately when it's in terms of what your learning is supposed to be on this. So please take the time to analyze and think through, and good luck. Bye.